All right, so I'm John Turner, Oak Ridge. A number of you have heard me speak. I've spoken over the years at these several times, and I'll mention that again. I wear a few hats as a group leader of computational engineering group. I've still got a title as part of CASEL, in which many of you have heard me talk about at these before. But today I'm going to talk about the Additive Manufacturing Project, which is part of the Exascale project that Paul and others talked about, and Tom as well earlier today. I've listed a bunch of the collaborators. This is a project that crosses Los Alamos, Livermore, Oak Ridge, and NIST. So I just wanted to list some of the people on the team there. So I'm going to tell you a little bit about additive manufacturing. I'm not sure how much you're aware of it. It's under rapid development over the last few years. And then you've already heard about the Exascale computing program, so I don't have to say much about that. And then I'll tell you about this project. I went back and I spoke right in this room 3 years ago at the 2014 HPC User Forum Meeting. And this is a slide I took out of that, and I talked about spent a little time on CASEL. The title of that talk was three projects that have strong industry connections, and the point was that all three had different levels of maturity, and I used that little stoplight chart to kind of give you an idea of community acceptance of HPC, of simulation, the maturity of the models, and maturity of the software and the funding landscape. And you can see that so CASEL was in pretty good shape. Another effort funded under EERE, the Vehicle Technologies, and Department of Transportation was our battery simulation effort. It's not quite as good as the nuclear energy story, but still pretty good. And then the new kid on the block at that point, this was 3 years ago, for us at least, was additive manufacturing. And you can see that there's a lot of red there in my stoplight chart. Not a lot of models, not a lot of software, and there really is a lot to go on from the welding community, but a ton has happened in the last 3 years, and so it's really hard to even imagine. The amount of literature and research that's happened over the last 3 years is just incredible. So it's kind of interesting to look back and see that. So I assume most of you are aware of what's happening, of what 3D printing and additive manufacturing is doing, but it started really taking off maybe 5 years ago or so with a lot of polymers and toys and things like that. Then you started seeing some medical applications, prosthetics and things like that, but still mostly metals. But really, what has taken off in the last few years is metals, and you see a couple of examples here, and the kind of things you can do with it, putting cooling channels inside, building a turbine blade with internal cooling channels designed in from the start. These robotic hands that you make the whole part in one fell swoop with internal machinery. This gives you a flavor of the kind of design possibilities, and this is pretty old. There's much cooler stuff now, but you start with a part like this that weighs this much, and you can cut pieces off and get down to something like this. But if you use a lattice structure, which you can make pretty easily with additive manufacturing, but it would be very difficult with other traditional processes, you can get down to a similar weight with much better performance. So basically the design space is really opened up with additive, and so there's a ton of excitement about this. And to show that it's, I went to a workshop down at Marshall Space Flight Center last August, and they gave us a tour of some of the facilities, and they've got these test stands where they build rockets and fire them off and test them out. And so this picture here has, I think there were seven or so parts, and I can't remember. I think some of them you just can't see in this picture that I took. But several of these fairly complex parts are additively manufactured, and they're the point of this is to show you that these aren't. It's really not a toy. I mean, there's some real application space. GE is making nozzles at production scale that are going into products. So it's really taking off. But what the downside, the real downside though, is that it takes a lot of trial and error right now to get from the making the part to the getting the actual what you need at the other end. And so I'll say a little more about that as we go on. So there are a bunch of different additive processes. Some of them use a powder feed. Some of them use wire feed. Some of them use a plasma. Some use an electron beam or a laser. All of them involve some sort of feedstock that's a basic material that's being melted, sintered, and melted to form the new whatever geometry you want to get out of it. So there are these melt pool technologies, direct metal deposition, where you're blowing the powder and melting it as it in flight as it goes and adheres to the new part. In this project, we're concentrating on powder bed technologies. So these start with a bed of powder. You spread out a bed of powder. I'll go into this in a little more detail. And then you melt it, and you put on another layer of powder and melt it again. The point of this slide is to show that really all of these technologies have a lot of physics in common. You're depositing energy on some base material. There's melting. There's solidification. There's evaporation, condensation, heat and mass transfer, and solid-solid state phase transformation. And these parts are repeatedly heated and cooled. So as you're building up these parts in the powder bed, they're going through cycles of melting and solidification. So it's very complex physically. It shares a lot of physics with welding, but not everything. Some of the solidification rates are different. There's a lot of things that are different. So it's a great problem and very complex geometries because of the design space. This just summarizes some of that. So if you think of it as a welding process, it's miles and miles of welding, which is very difficult to do. Large temperature gradients, rapid heating and cooling, those are some other things that are a little different than most welding processes. And also, so it shares some physics with casting as well, but again, different solidification rates and different gradients. Heterogeneous, multi-scale, and there's a lot of parameters and really an incomplete understanding of how they all link together. So I wanted to show, this is one of the machines we use at Oak Ridge quite a bit. It's Arcam, which is a company that was really at the forefront of the electron beam technology. They've now been bought by GE. GE also bought one of the premier laser manufacturers, so they're really aggressive in this area. So what happens is you start with a 3D CAD model. It gets sliced into 2D layers. Send that to the machine, which is, you've got a picture over here with the beam up there, a table down here with the powder on it, and then the powder sitting in here and gets scooped out there. In each layer, you like I said, you lay out a layer, you preheat it, basically a sintering step. Then you do another pass that actually does the melting. Then you put on another layer, and the table actually descends as you build it up, and you end up at the end with a part. So the traditional way that the beam moves is in a line across the part that you're building. I'll mention why that's important in a second. And at least up to a couple of years ago, and still, the knowledge has improved, but there's still some lacking elements. But the way to manipulate the microstructure via the process has not been well understood. We've come a long way. But what people saw was that as you build this, you'd get columnar grains in the build direction. And so, long story short, at Oak Ridge, we've been able to come up with, and other people have replicated this now, we've come up with some scan strategies where we're able to manipulate and get grain structures, either columnar or equiaxed, in different locations depending on how you drive the beam. So there's whole talks we could do on how you do that, but basically you go to a scan strategy that's doing spots strategically, in sequences that are predetermined, rather than doing just a back and forth line. So the reason I go into that is it's not intuitive at all. And it was really benefited by simulation. And if I have time, I'll go into what that really means. But the way that was done was by controlling the solidification rate, so the characteristics of the melt pool as it's being developed. And so it's really kind of a holy grail of manufacturing, is to have that kind of local control. So you can imagine, as you're building a part, you can actually determine the grain structure anywhere in the part. Now what we haven't done, kind of the next step, is to orient the grains. So those columnar grains, you'd like to be able to get them in any direction you want, because obviously your strength, your parameters, your properties are different depending on on how those columnar grains are oriented. Right now we just focused on the columnar and equiaxed. So I included a couple of simulations here before we get to the project itself, to give you a little more understanding of how this looks. Let me see, how do I play this? So this is a simulation from Lawrence Livermore using their L3D code that's done a fantastic job of simulating the interaction of this is actually a laser process, laser with the powder bed. And there's whole talks about this too, and how this really matches the experiments well, and you can get a better idea. What you're trying to understand here is the porosity. One of the major defects that you find in additive is porosity, and also as the laser moves, you can get spatter. The powder particles will get, or the droplets will get sent off and cause defects in other parts of the build. But this is a very expensive calculation. So this I believe it was tens of thousands of processors for days at a time of compute. So a fairly serious calculation, and just for this, just a few millimeters of the build. And we really want to be able to simulate an entire part, building an entire part. Okay, so at the other end of the scale, we have, this is also a Livermore simulation using Diablo. And on the left, you see the material moving from the powder, which is blue, to red, which is consolidated, or it could be melted or solidified. It's just a consolidated material. On the right, you're seeing the stress, and if you look, I don't know how well you can see this, but you can kind of see it breathing, due to the residual stress as it's heating and cooling with each layer, and you can see as the part's built up, you get these stresses within the part. This is the base on which the part's built, and you can see, I think at the end of this, we actually cut the part off the base, and you can see some of the stress be relieved as that happens. So this is a great calculation. This wasn't actually that expensive, but it's got a lot of homogenization. Those layers that you're seeing are really they correspond to about 20 actual layers of a build. So it's really a fairly averaged calculation. It does a good job, and it gets a very good answer compared to to experiment, but it's still not nearly at the level that we'd like to see. So really what we're trying to do is bring those two levels together and actually add the mesoscale level, which I don't know if I'll have time to go much into detail, but I'll at least mention it. But this is what we'd like to be able to do, is build entire parts with a full understanding of, specify the process parameters at the beginning to get the desired property part at the very end. And really that's the performance level. So this is showing you the, cutting through that part after it's built and looking at the simulated stress on the right versus an experimentally determined stress. So it does a pretty good job. So one of the things that people have found in making these parts is that this gets back to that columnar grain structure in vertical. When you just use the standard scan strategy, you get columnar grains and you get a lot of anisotropy in the properties. And so this is one of the things that led to that desire to get the equiaxed in parts and columnar and other parts. But this also demonstrates how these additively manufactured parts, even using the exact same materials, get very different properties because of the process parameters. What this is comparing is from cast plus HIP, which is a post-processing step that's often used, and wrought and annealed. And you can see how the additively manufactured parts have quite different properties. So there's both a pro and the con there. It means that you can adjust, if you can adjust that and get different values, that's a benefit. Okay, so as I said, what we really want to do is get a linkage between the microscale structure, which is driven by the process parameters, and the ultimate properties and performance of the part. And so you can see that we've got different areas of physics, different scales, from the powder dynamics to the microstructure, and then to the ultimate full-scale part. And really, at this point, there's no single code that can do all of this. And so what we've started with is a collection of codes from the labs that have different aspects of the physics that already typically run in parallel, but may have different degrees of scalability, and we're bringing them together into a single environment to work together on this problem. Okay, so I don't have to spend too much time on this. I think most people were here to hear Paul's discussion of the Exascale computing project. 10-year project, I think now it's 7 years, as he said, 50 times the performance, a power envelope of 20 to 30 megawatts, and it's a broad program project that includes these 4 areas: application development, software technology, hardware technology, and then acquisition of some of the early testbed systems and the early Exascale systems. So I'm going to talk all about the application. So application area. So similar to Tom Evans' talk earlier. So he's part of the same basket of applications being developed for these new systems. So it's one of the 15 projects that's funded under that application area. As I said, the partners are Lawrence Livermore, Los Alamos, and NIST, along with Oak Ridge. And I'll skip those details because I'd like to get to... So I wanted to show this one, which is goals are to accelerate the adoption of additive by making it more possible to design and get to a qualified part faster. That's really the ultimate goal. So minimize the trial and error that takes place right now in building a part, adjusting the parameters, which can include the preheat temperatures, the background temperatures, the beam diameter, beam speed. There's just a ton of them that you can adjust. And ultimately allow a part designer, to come up with specify location-specific properties to get the performance they want. And we're going to do that by coupling high-fidelity subgrid simulations, mesoscale simulations, within continuum models that can do the melting, solidification, residual stress, so continuum level simulations to get more accurate local properties, and then ultimately more accurate, full parts. Got a huge set of numerical dependencies, library dependencies, a mixture of C++ and Fortran between these codes. If you're familiar with some of these code names, at the continuum level, it's AL3D, Diablo, and Truchas, which is a casting code from Los Alamos. At the mesoscale, AMP, MEUMAPPS, and TUSIS. As I said, some of these are C++, some are Fortran. If you're familiar with the set of motifs or dwarfs that Berkeley's come up with, if you look across this set of 6 physics components, we hit a bunch of them: sparse linear algebra, dense linear algebra, spectral methods, unstructured grids, dynamic programs, and particles. Now, I did want to mention a couple of things that are currently outside the scope of this particular project. We're not doing the powder properties and spreading. There are people doing that, and it's an important part of the problem. Shape and topology optimization, really what we're doing would feed into a larger optimization loop on shape and topology optimization. We're not doing the post-processing. We're not doing data analytics and machine learning. There's some really cool stuff happening there, taking in data from a build and correlating that with success and failure of a build. Ultimately, we see the physics simulation linking with the data analytics to do a better, to be better, joined together. Reduced order models, there are plenty of people doing that. We ultimately think we could use these simulations to lead to better reduced order models, but that's not what we're doing. We're looking at the high fidelity. This is our picture of that process map, and you can see I've grayed out the things we're not doing, and we're focusing on that process-aware part. Melt pool scale, the part scale, those feed into the microstructure modeling and then property modeling. And I've got another version of that picture that has the code names added onto there. So you see the mesoscale phase field codes down at the bottom, and then the continuum level at the process scale. I'll probably wrap up with this slide. Maybe I have one or two more. But this gives you a summary of those 6 codes, the 6 physics components that I mentioned, the continuum levels, continuum codes at the top, the mesoscale at the bottom, and where they fit in. A couple of things to notice. I already mentioned some are Fortran, some are C++. Big dependency on Hyper, which is a library out of Livermore, solver, preconditioned solver library. Several of these have proxy apps or mini apps that we can use to share with the software technologies people and the co-design and the hardware people to do optimization on and collaborate in a co-design fashion with. One question you might have is why we have 3 different phase field codes. You can see that although they're all phase field, they take very different approaches to the problem. A spectral code, a finite volume code, and a finite element code, each with different strengths and different in the physics realm. So I think I'll skip. This was more detail about how we do the microstructure control or the grain structure, but I think I'm pretty out of time. Let me say one thing about a key part is we want to fire off the phase field calculations, the mesoscale calculations dynamically, so that we're not building a static database assuming temperatures or conditions and then interpolating, but rather getting conditions as the process in real time, in simulation time as the process evolves. So I think that's something new that's going to be a stretch, but having those subgrid calculations happen dynamically during the process. And that's one way we think that we can really leverage the Exascale capabilities. So I'll stop there.
Great, thank you. Any questions?
Well, I'll have the first one. I have the mic. On the Arcam system, what's the line resolution in X, Y, and what's the layer resolution in Z? And are you happy with those numbers, or would you envision new designs being made available if those
Yes.
numbers were improved?
Yeah, so that stuff is it. So those values vary dramatically fairly dramatically between the wire-based, the laser-based, and the electron-based. The layers themselves are roughly tens of microns, and that's pretty good. The XY resolution is really small. It's its electron beam is very tightly focused, so that's very good. That kind of stuff is actually very good. One big difference between laser and electron beam, the electron beam you can move from place to place. We can do that spot melting because it's not a mechanical system moving the beam, and so you can almost instantaneously move anywhere on the part. Whereas a laser, it's being focused, and it's much slower to move. But there are those kind of trade-offs between electron and laser all over the place. But it's a great question. The machines themselves are improving all the time. A problem is that they're typically black boxes, and so it's very hard to get inside and learn about those process parameters and which ones you can control and which ones you can't. Arcam is one that we over the years developed a really good relationship and kind of got under the covers and got real good access to their programming, and we're able to do a lot more manipulation of the process parameters than other machines, and it's one reason we really like it. NIST is building its own machine that will be more open architecture, and that'll be fun to play with.
So John, you mentioned how porous the material ends up being. Can you make gas-tight parts with this?
Porosity is a problem, but it's not like these are really porous parts. It's just that they can have pockets of porosity, which can affect the strength properties.
I'm thinking like nozzles for some hydrogen burning thing.
Yeah. You can make sealed.
Okay. Thanks.
Yeah.
John, that was fascinating. By the way, to that question, we've actually GE's built parts for hydrogen additively. They do seal gas.
Yeah.
So, but my question to you is this: you're trying to link a lot of different classes and layers of software into a design loop. How do you envision actually accomplishing that? Because they're multidimensional. And what are the gaps? What are the things that are missing that if you had them, that would make that kind of multi-physical problem easier to go attack in a fast, iterative way?
There's a pretty long answer to that question. If I were looking at that, if we hadn't done Castle before this, I would say this is ridiculous. It's a crazy thing to even think about trying to do. But it's very similar to what we did in Castle was linking different codes that had different physics. And actually through Castle, we built some tools that do like solution mapping between physics fields of between different physics components that may be on completely different meshes. So we'll leverage some tools like that were built for other applications. But yeah, putting this into an overall usable environment or tool is no doubt is going to be a challenge. So we're trying to pick off pieces of it, get a couple of components talking together, and just evolve into an environment where you can do the full thing. It's definitely a challenge, but we can talk more offline. We're probably out over time.